looking at the slender columns for the composite columns. And this is what we have here is that just an introduction. Last week we talked about the short column, so the member it doesn't buckle, so it's very good remain straightness in the geometry. But once you have the ratio of the width of the section of the column section to the total length of the member become really bad, or we talk about the term of the L over R, which is the standard ratio of the column that we use all the time, become very large. The capacity of the member rather it can achieve the maximum capacity of the section, it cannot do so, it has to drop, right? And how we take into account of the drop or the reduction of this capacity, we have to use some factor to take into account. In this diagram here is about the buckling theories. This is the linear buckling theory that you have learned in the undergraduate degrees. So basically we call them as the Euler buckling, right? So the way how it works is this: you have initially you have the straight columns, and when you apply the normal force, what is happened, the axial force, the column, it doesn't remain shortened, so it start to form the nonlinear, so it start to bend to the sideway. So we have the out of plane action. When it's formed the out of plane action, so what is happened? So is we have the survey, and this is called as the member surveys, or we call as a small data. The small data is the secondary survey or the member survey that is from the column, because the column is by theoretical, when it taken the axial force, it should deform in the column line. So basically it should deform along the line of the member as a shortening, but because it's too slender, rather it's from the deformation along the line here, it start to form the out of plane actions, and we call the small delta that this is the out of plane deformation. For the out of plane deformations, when if you take into the equilibrium equation, right? So everyone know in that if you have the out of plane, and if I cut the cross section somewhere here, right? So what I see is this. So what I would say, this is the axial force, and the axial force has been to satisfy the equilibrium. We have the axial force here, but the line of the column is supposed to be in this line here. So that's why what has happened, you have the eccentricities in the member, and we call this amount of the eccentricity as a out of plane deformation, and the amount of the out of plane deformation is equal to the delta naught plus delta. The value of the delta naught is, we call them as an initial imperfection. So normally when we have the column come from the manufacturing, we not always have the very straight column, which have some deviation, and this we call them as an initial imperfection. Oh, I didn't upload the slides. Sorry, I will do so. Thanks for telling me. I thought I have done so. If you can just, I think I did it. Let me check. You can just wait for a second. The week, okay. I didn't upload the week number 7, but I thought I did. Okay, just wait for me 2 minutes. Okay, it's done. So you should have it now in your my course view. Okay, so thanks for telling. So what is happened when we have the member eccentricity, we call as a secondary effects, right? And this somehow will create what is called as a secondary moment, which is the moment that we didn't apply to, but it still comes. And this amount of the moment, we call them as an n time with the data node plus data, right? And when we check the stress, so you're seeing that, okay, when there is the eccentricities of, which is the secondary moment, the problem is that the column, it doesn't remain stressed at all. It start to form the curve. Then we use the, what is called the Euler-Bucking theories to assume this is the values of the eccentricity and so on in the sine curve. And when we can derive them, right? If you want to see the derivative of this, we can derive the derivation of this, we can derive them to obtain the Euler-Bucking. So this is the first mode of the buckling. So what it means, if you recall, is that the Euler-Bucking, they can form the curve, which is the first mode is here, and you have the second mode, right? And you have the third mode, and so on. And in the Euler-Bucking, they're saying that in the first mode, they take n equal to 1. This is the second mode shape, and this is the third mode shape, and so on. They're saying that the more that you have the bending curve, right? For example, this one is at the start, at the end point. This one you have two other bending curve. This is a single bending curve. This is double. This is a triple, and you can have more. The critical one is that when it's from the shape, the critical Euler-Bucking is when you have the first mode. So when n is equal to 1. That's why you have this formulation. So it's saying that the bucking is appear as first when the column reach this curve here, right? So it will not go to the second mode because it will fail according to the first mode first. So that's why in the Euler-Bucking, they take from the mode number 1, right? I suggest you, if you interested, you can have, look how we derive them, very simple by using the size equations, right? And there is a book in the mechanics of solid that derive them for you. And so what we do, they give, okay, this is the critical, this called that this is the critical axial force capacity that can make the linear elastic column to fail. When it's failed according to what is called as a geometry. The shape of the member has been deformed too much, then it's failed, right? And when we derive them, it's based on the boundary condition where you're having the pin connections here and you have another pin here. So that's why the length of the member that they use and they derive this equation is coming from this curve. And they're saying that, okay, if you have the different boundary condition, for example, you're having this of the support, or you having this type of the support, you have the pin, loader and pin, you have the fixed support here, we have the restrained moment and the fixed support at the bottom. We still can take this equation, but we should adjust them to match with the boundary condition that it has by changing the value of the length. And the length that we change, we call them that we have to use what is called as an effective length. And this is come as from the effective length concept. I didn't go too much on this, but I just like to emphasize, just to tell you the concept, and that we read to, and it's quite reasonable why we have to adjust in the code. And the code always refers to the Euler-Bucking, but they have some modification or modified factor to the Euler-Bucking formulation, right? Before we go to the formulation, let's have a look at the graph here. The Euler-Bucking formulation, if we want to identify the failures of the column, And the failure that we look at, we assume that it's just the squash load only, and we're not looking at the combination with the moment as yet, right? By looking at the linear elastic theories or the elastic buckling theory of the column alone, the Euler buckling that we have in the formulation that we just talked before is giving us this curve. And this curve has been plotted according, right? I hope it's matched the curve well. And this curve has been plotted should be very close. Okay, that's fine. According to the Euler buckling formulation, and if you recall, they're saying that n critical equal to the pi square EI over L E, right? And this coming from the Euler buckling formulation, and that formulation is give the failure line according to this curve. And if we calculate the squash load is mean we start to take into account of the material property of the steel. The squash load that we have in the previous example is saying that the squash load capacities, it doesn't matter how slender of the member we're looking at, we saying that the capacity is a flat and it's a constant, which is the n, which is called as a n SQ. And if we compare with the n critical, we might see that at some by theoretical at some levels, at some level here, you would see that if you have the length of the member as an x-axis, normally we use L over R as a standard ratios. And the length of the member the member is so short. The thing that is governed is the capacity of the material property, which is the rigid plastic property. When the length become increasing according to the line that I'm moving them here above the critical length, right? The value of the squash load that we have as a fix will sit above the buckling load. When it sit above the buckling load by the design, it will fail according to the buckling before it reached the rigid plastic capacity of the cross section. So that's why we make the cut or make the discretization of the line here. And we saying that by theoretically that anything that for the column that having the length more than the critical line here, the governing criteria become from Euler buckling. And when the length of the member sit or less than the critical line or the critical length, we're saying that it will fail according to the rigid plastics. Theories. Right, so that's why normally what we're supposed to see for the theoretical buckling condition is that we compare between the squash loss and also the buckling loss. And that we will see that, okay, when the length of the member or the slenderness of the member it reached or is slender to some value, we call as it's got the limit of them, which is at the plastic limit and the lean elastic limit, right? When it sit above the plastic limit, right, we drop the capacity from the squash load. When it reach the elastic limit, we drop further. This is coming from the reason is because of it can't buckle according to the geometry effect or the secondary effect. It doesn't come from the material property, right? And this is by theoretical. But if we looking at the realities of maybe obtained from what's it called from the test or the experiments, we finding that the curve that it failed, it doesn't follow the curve that I just discussed with you here. So it doesn't follow the failure lines here. So basically, when we do the real test, it has some slide or some certain value that sit below to what we think it should be. So that's why in the code, they refer first to the critical buckling, but they have some modification factors applied to because of the concept of at the realities. There are some other of the effects that influence the buckling, right? And that it might be the lateral torsional buckling that you might have some other factor add on and so on, right? So then they start to discuss about the linear elastic column, and they say that okay, they want to try to obtain this curve when it reached the first yield. So before it's formed the rigid plastic capacity, and it's also take into account of the buckling or the secondary effects, as I mentioned before. And they have derived it from the Euler buckling formulation until they obtain this approximation. The approximation of the elastic column is as follows. They take the assumption that the stress that developed in the cross section it reached at the maximum is U, right? Why we saying that is this? Remember that if we have the column that's subject to the geometry buckling, right? We have remember that we have this diagram before. And we have the eccentricities. Which is the data node plus data. And you know that this will give you the secondary moment. Which is equal to n times with the data node plus data. And if I like to calculate the stress, right, when I want to calculate the stress value at this point here, so it is a combination the stress value is coming from the combined of the n alone and the bending, which is the secondary moment. So when we're looking at the value of the elastic stress, it is n over the areas plus and minus bending moment over C. And I'm saying that this has to be less than equal to the U. That's why we're saying that this is the elastic, right? When it just reached the U. And if we push the limit of these combined stress values to the U, and we derive by using the buckling formulation, we will obtain the curve. Sorry, let me go back. We obtain this curve here. When we obtain this curve, right, there is some modification to the equation. So what we're looking at is this. Let me cut the curve and I just plug them here. It's very small. Okay, if you're looking at in these equations, what you can notice is that it's based on the fraction of the squash load. The squash load is the line here. And it has some factors. The factor has been written in the bracket as a ratio of NE, right, over N squash load and the epsilon. The epsilon has been given by this formulation and in terms of the eta terms, right? And this has been written in terms of the initial imperfection, which is the data node, times with the width of the columns, and divided by IR, which is the radius of gyration. So you have a series of the formulation, right? You can substitute them easily. And how is this formulation is giving you is this? The formulation that we're describing is just approximate the first yield capacities of the column, which is the line here. So you might have the reductions from the squash load capacity, and the reduction capacity from the squash load has been given by the term in the bracket. The more that you have the slenderness of the length of the member over R, which is the radius of gyrations, to be more, the more of the capacity that you would have from this one here. So basically, this capacity is telling you the dropping in fraction of the squash load. So the more that the column becomes slender, the more of the less, sorry, not the more, the less of the factor of this will become, because this is the reduction capacity. So it's mean the Morning gap that you have here, right? So that's why we can approximate the linear bucking capacity by using this line, but of course this is quite conservative because we didn't use the capacity up to the fully rigid plastic. We just use up to the elastic, right? The yield, the first yield of the column. And we normally don't use this one in the code, but we having them, right, to explain. And in this concept, they're saying that you finding the factors, which is the psi factors, which is we call them as the slenderness parameters. The slender or the psi factor, they're taken from these equations here, right? And you can approximate them. And this is the example that they're looking at. Okay, you have the thin bar, right, which is the solid, not the composite, the solid steel, which is the rectangular steel bar having the width of 20 centimeter and the thickness is 2 centimeters. And they're asking, by using the elastic bucking theories, can we approximate the column capacity? So what we do, you can have a look, you just find the value of the curses, the eta, the curse, and you find the reduction capacity or the psi factors here. And that you just compare between the capacity after it's buckled in the first yield, compare with the squash load. You're seeing that the difference is quite a lot. When the difference, if you want to determine, right, because we're saying that the ny equal to the psi time with the n squash load, right? And in this case, you're having the reduction parameters equal to 377 divided by 1,200. So you're looking at around 25% left. So the reduction is 25%, right? Approximately. So you can do this. This is quite straightforward. I not go through the details, right? Because this is the buckling capacity, the Euler buckling, and this is the squash load. So you just very simple following these formulations here, and you will have the elastic the buckling capacity at the first yield. And we don't use it in the code, but this just to explain to us that how can they approximate the secondary effects or the buckling capacity. And the second example the same, but just to change the value of the effective length from L equal to the K equal to 1 to be half of this. So basically you having the KE to be less, right? And the critical load you will have more, right? The only difference is these terms. This is, to me, it's not a big deal. And we not go to the detail. I leave for you. If you're interested, you can read it, right? So what we're going to discuss, and and it has been used in the code, is from the page here. So it's first, let's discuss about the concept of the effective length. The reason of the effective length is we can use it for the critical buckling equation when the boundary condition of the column has been changed, right? The effective length equal to 1 when you have double pin, right? One is a roller, the other is a pin connection. When we have the effective length equal to 1. The more that you restrain, if you restrain them, you can just subdivide. So basically in this point, it gives you the contraflexure point. So it has the zero moment, right? When you have the double curvatures, you have these three of the zero bending moment point, then the effective length can be divided by half. When you have more or different boundary condition, for example, you have the fixed end at the bottom, you have the roller at the top, the effective length will become better, so it's become less. The less of the effective length is the better, because you don't have to be subject to much of the buckling equation or the member buckling, right? When you have the fixed end, this is the worst case. You have the fixed end here, and you have the release end, so it's a free end at the other side, so the effective length become 2 times, and this is one of the worst case. So that's why when we have to design the cantilever column, which has been straight high, and the end at the top have been free, right? It's will more likely fail according to the geometry buckling, because of it reduce or it's increase the effective length by twice, and it will reduce the buckling force or the buckling capacity more than half by 4 times, right? And this is explaining before we start to looking at the code, you have to define whether the structure that we look at has been subjected to the slender column or not. Similar to the standard steel code, we have to check the ratio of the slenderness we call as a L E over R, right? This is called as a slenderness ratio, and you'll be having an unbreasted and the breasted columns. The unbreasted column is mean into this diagram, so the column can be swayed, right? If the column cannot be swayed, so you have the non-sway, or you restrain the sway by some mechanisms, right? For example, you have the building which come with so many bay, so it's unlikely that it will be swayed, right? In this case, you can increase the level or the value of to check for the buckling, and L E over R had to be less than or equal to this equation, right? And when we discuss about the braced columns, this is I over R, this is for 0.25D, this is for the typical rectangular column, so we can use this. And what has happened is normally it had to be written in terms of the ratio, similar to the steel standard, M star 1 divided by M star 2, and we having these ratios here. So you might see that to check only the slenderness, the first thing of all, you have to calculate the NU node. The NU node, where it's from, right? The NU node, if you're looking at, we have the way how we do the calculations. Let me check first. And let me see the code. Just hold on for a second. I think by definition, the NU node is a squash load, right? Capacity. But I will tell you. But let me check it. The ratio of the M1 divided by M2 is this. In the column. So I finish on this page then. Assume that you having the columns here. And when you're looking at each of the column, the force is coming first is axial force. And the second is might come with the bending. They're saying that M, if you assume this is M1, this is M2, M1 must be always less than or equal to M2. So it doesn't matter whether the top column or the bottom column, which one is got the value is more. But if you're finding that the top one is giving you more, it has been transferred with the more bending moment. So you have to swap, right? This is become M2 and M1. So basically M2 has to be always greater than M1, right? And they're saying that the ratios of the M star 1 and M star 2, it is negative. It's take the negative value if you have the single curvature, and it's take the positive value if you have the double curvature, right? And this will be discussed this possibly when we meet it on, similar to what we have for the steel, right? When we calculate the moment magnifiers. So we will come and discuss about this. And for the time being, let me stop at this point. Okay, hi guys. Excuse me. What we have left, and this is the last topic of our talk for the whole half semester. We're talking about the designs of the columns, and in the design of the column, we already talked about how can we obtain what is called as a section capacity. Before we come in and talk a bit on this, I think it would be nice if we can just briefly discuss about the concept. When we talk about the column design, in the column design, and in which is most likely similar to most of the designs, we of course we use the limit state design conditions, and for the ultimate strength designs, and which is most of the cases governed in the columns, we talk about this equation, and this will be used a lot. Sorry about my voice today. I got the allergies in the morning. So what has happened? So in any of the limit state designs, they say that this equation has been used to check the strength capacity of any member that you're looking at. So let me remove the noise. And in the strength capacity, we're saying that if we have the column, which is any chair, for example, we might looking at the rectangular column, we may look at the circular columns. We might look at the infills in which you have the steel member or the encasted. And in which what has been most popular used, excuse me, more likely is the the infills has been very popularly used. This is the infill. Assuming that the red one is the steel member, and you have the concrete fill inside the column, right? So one is the encasted, the other one is the infill. The difference in the property of these two concrete is that these two type the column. Let me list it down. In this one, the steel member doesn't buckle. Because the section of the steel has been enveloped by the concrete, so it's prevent the buckling, right? So this is the nice property of it. However, for the concrete, it's still, even though it just come with the partial confinement. On the other hand, for the infill, right? The infill, the steel member is subject to, it just says can establish local failures, which is we call as a local buckling. The nice things of the concrete is fully confined. Right, so we have two types of maybe decided column, and this has been most popularly used in the industry and in our structural designs. So the difference between them, of course, they offer the different benefit. So what I try to rearrange that. Okay. So when we talk about this, the formulation that we use to calculate what is called as a squash load, and we call them as a N. If you have a look in the previous page, here is a NUO, which is at the squash load. SQ. Right. The formulation is for the encasted, we use 0.85 of the F prime C times AC. And we add them with the Fy times AS. Right, and in this case, steel section is compact. Doesn't, as I said before, locally buckle. But if we looking at on the other side, the NUO, let me remove this because it's we can take the full capacity of the concrete but for the AS we have to check local buckling. And if indicator is buckle, you have to use the BE, right? Which is the B effective. And how we check that? We take the ratio of B over T times with the square root Fy divided by 250 and less than the limit, right? And we call them as the EP, which is the lambda, the limit for the slenderness. So EY. So we check this, and if it's above, then this limit, so you have to reduce the section and you have to calculate the effective width according to what we discussed in the last couple of days. So the thing that we discussed here is just only for what is called as a section capacity. So when we're looking at the design scenarios, in most of the standard design that there has been proposed that in the specification, and we keep using this. When they talk about the ultimate strength criteria, when we discuss about the ultimate strength, they mention two types of the strength. One is a section capacity. When we discuss about the section capacity, so this is mean what we talk about into this, right? And this including the interaction diagrams, which is we have been discussed it. So you need to obtain the diagrams and you identify the failure lines, right? And in some of, if you use in the code, they also say that you can simplify them by just take 4 of the point and you just simply connect the line between these 4 points, which is A, B, C, and D, right? And this is we call them as interaction diagrams. And the best when you plot the interaction diagram, what I suggest you're looking at, you take what is called as a reduction capacity for the axial force, and you time with the NU. And in this case, you take the reduction capacity for the pure bending, and you time with the MU, right? And when we discuss about the section capacity, we assuming that the member it doesn't buckle. When the member it doesn't buckle, so that we can take the full cross-section property. So what it means if you take into these considerations, you having the point, which is the column might subject to both the axial force. And when we discuss the forces that apply to the column, we always mention to where is formed at the plastic centroid. So remember, in all the scenario in this case, if it's symmetry, it is just a coincidence that the plastic centroid is sit in the same centroids of the geometry of the cross section. But if it doesn't, so you have to find where is the plastic centroid. Right, and the forces that we discussed has to apply to the plastic centroid, right? And we call them, this is the applies forces, which is the axial force, and you have the bending moment as well. And you just have a check, and don't forget that these two have to time the factor load as well. And you just check whether the combinations of the bending moment and the axial force has been well sit inside the envelope or not. If it does, so it's good. So that's why if we connect the line between the 0 and we just connect to the point when you apply the force, so we call them, this is the loading lines. And it's a linear because it's simply that you can easily say that E, it is equal to M star divided by N star. Excuse me. Right. So in the section capacity, we always have the linear loading lines because it doesn't have any of the member buckling or the failures according to the geometry of the column or the stress net of the column to become involved. In our discussion, as what we start to talk today, we talk about the capacity of the column in terms of the member. When we talk about the member capacity, if you recall when you did the design in board of the concrete and in board of the steel, they try to reduce the capacity, which is at the envelope here, in some fraction. In the concrete design, they keep the envelope, the interaction envelope as it is, but they try to magnify, so they enlarge the value of the bending moment and the axial force by using the moment magnifier concept. So in this concept, basically they transforms the geometry imperfection and also the secondary effects according to the bucking shape of the column to become the secondary moment and of course the secondary force as well. It depends whether the problem you're looking at it is restrained from a sway or is unrestrained from the sway, right? If it's restrained from the sway, the discussion that we discussed it now is work. If it doesn't, of course, you can go back and look in the concrete. They have another way that they take into account what's it called as the of a unsway of the sway column, right? So we go back and talk about this again. But if you look into the steel standard, the steel code, because it's prone to the buckling is quite severe. The buckling is mean it doesn't only come with the section buckling, it have the member buckling as well. So that's why if we have a look in the concrete code, the steel code, they always plot the curve, which is they call as this is the capacity code. Sorry, this is the capacity line here. For example, we having this is the axial force capacity. So I say this is the 5 MU, right? And they're saying that if you calculate from the section capacity or the yield, it's reached the section capacity at the most, and we adjust them according to the effective weight which is take into account of the buckling criteria. So these have been coming from, let's change the colors. This consideration. And any capacity you have and seen as a flat line, and they plot against in the diagram as a slenderness ratio, which is L over R. We call them as a slenderness ratio. And don't forget that we have to adjust the value of the length by using the effective length. We call along this line here as a section capacity. And they have another line as well. And in this line here is coming from let me shift a bit to the right hand side. The calculation of this equation typically is coming from the Euler buckling. And the Euler buckling formulation, what it has been told, is talking about the imperfection or non-stressless of columns geometry. So what is really mean is that when we having, so let me write down here. Sorry that I have to swap the page quite a lot. We have, assuming we have this column, and the boundary condition of the column as usual. And we got the force, right? And what is happening? This is the ideal column that we should have is a straight line, very nice stressless columns. But somehow the initial condition that it came is have what is called as an initial imperfection. And when we load the force, the axial force further, this initial imperfection start to enlarge more. So that's why we have in this as another lateral deformation. So the value of the lateral deformation that we have here, we make the column to become imperfect. The imperfects come from this, sorry, the imperfects come from here, and non-stressless, of course, start from the data node. And this as a result of the secondary moment. Because when you apply the force, there is the sway in the member. So when you push the member more, the sway start to enlarge, and the value of the data here, we call them as a secondary effects, which is the out of plane action. Or we call them as a secondary. Right. And according to this, I try to rearrange the page well. So in the steel cord, they say that you have to find the capacity, which is a NM, which is the member capacity. This has been told in the steel cord. And if you recall what we have in the steel cord, the envelope of the curve here, they said the slide is slightly sit below, but they're saying that, okay, you may have the section capacities here, and you have the elastic and the inelastic lines. So this is come and sits behind what is called the Euler buckling, because they're saying that the theoretical Euler buckling is quite too not conservative, but it's overestimate the strength. So that's why they have to adjust the secondary effect a bit more. So what is happened, the graph that we see over here, they talk about the capacity under the NM. So you might see that in order to take into account of what is called as a member capacity, to calculate, to approximate the member capacity, for both the concrete and the steel design, they got different concepts. The concrete, they use the concept of the moment magnifiers in the concrete designs, so they don't reduce the capacity of the member by looking at the member capacity. They use the section capacity. But in the steel designs, they reduce, they drop out the member, the section capacity to some certain value, and they call them as the member capacity. And if we discuss about the steel designs, they're saying that the capacity of the columns that we are looking for is a minimum between the section capacity and what is called as a member capacity. You look in the steel code, they keep talking about this. But in the concrete design, we don't have this adjustment for the member capacity, because the reason for this, because the concrete, when it's taking the compression force, it is the favor of the concrete material, because the concrete can take the compression well. The concrete doesn't like the tension. The steel can be favor for the tension force, but it doesn't be well if we have to use them to take up the compression force, because the problem with the steel, because it's so thin compared with the geometry of them, when there is a compression force, it's easily to make the steel member to lose its initial shape. The lose initial shape is mean if the initial shape is a straight line, is from the buckling, so it loses the stressness. When it loses the stressness, it create what is called as a out of plane, or what we call normally as a secondary effect. The term of the secondary effect has been used a lot in the design, not only for the steel, the concrete. We talk in terms of the pre-stressed concrete as well. You already learned the concept of the pre-stressed concrete. Normally, when we define the primary effect is the effect of the applied forces that you have. The secondary effect is coming from the geometry, which we cannot describe them in terms of the applied force. So we call them as a secondary effects. So you might see the correlations, right, in terms of the designs. So because the composite steel and the column, we mix two material together, and we make these two materials to have the mechanism that they can work very well together. And we use the strength criteria to tell whether how much of the stress will be developed in each of the material. We have two types of the material. One is a steel, the other one is a concrete. So we go back and think about what we have done in the last 6 to 7 weeks. We just keep talking about, we start from the strain and we look for the stress. We transform the stress that distribute to each of the materials by taking the areas underneath the stress, transform them to be the force applied to the centroid of the stress diagrams, give you the force, and then you calculate the bending. right? It depends on you want to have the pure bending force. You take the sum of the axial force to be zero, because in the pure bending, or when we design the slabs, or when we design the beams, we just talk about the pure bending conditions. But when we talk about the column, it had to come with a combination of the axial force and also the bending moment. Of course, we have to determine where the axial force should be applied. So that's why we come with the concept of what is called as a plastic centroid. So we're saying that the applied force always go to the plastic centroid. So if it has some deviation from the plastic centroids, or it's come with the eccentricity, so we take into account of those force in terms of the moment, right? So that's why you have the combinations of the axial force and the bending moment, and we can use this concept to calculate the capacity when we try to remove, or we will try to rearrange the line of the plastic neutral acids. The plastic neutral acid, we tell where is the line that discrete between the compressive stress and also the tensile stress. So we just keep changing the level of the plastic neutral acids. So the more that you change, the smoother that you have in the curve. But if you consider only 3 levels of the plastic neutral acids, which can be used as an approximate diagram, we call as a piecewise linear diagrams. You will obtain the purple lines here. But if you just vary the plastic neutral acids line, the level of this between the full axial force and the pure bending, you just vary between them. And if you make them to have the point enough, you will obtain the nonlinear curve, we call as a nonlinear diagram, right? And we use this diagram to check the section capacity. And in our discussions, to what we try to looking at in this week, right? And I think I prefer to talk with you a bit more on the overview of what we look for. We try to approximate the buckling capacity, and this term we talk about in terms of the member buckling. Then if we understand this concept, we go back, starting from what we discussed it in our calculation. We're saying that if we talk about the elastic analysis is mean we're assuming that all the stresses that develop in the composite section doesn't sit above U, just hit the U stress. And we can use this concept. So this is our assumption that when we talk about the combined stresses, the maximum stress that can be achieved that just hit the U. So basically the stress diagrams that develop through the cross section still form the triangle stress, is not the rigid rectangular stress block as what we discussed for the maximum capacity. So if we talk about this concept, right, they say that we can adjust the values of the what's it called, the compression capacity, by having some type of the reduction capacity. The reduction capacity, so what it means, they're saying that the column wind is fail, right? If the slenderness of the member, which is the L over R, it doesn't mean the value which is so high, so it doesn't sit above the limit for the slenderness ratio. So we can take them as a full squash load. When we can take them as a full squash load, and how it's involved with these diagrams here, sorry, let me come back to this diagram again. If theoretically, if it doesn't sit above the limit here, we always check for what is called the slenderness ratio of the member. But if it doesn't sit above the limit has been told here, basically we say that which is good, so we can use the capacity of the squash load. When we talk about the squash load, we refer back to what is called as a section capacity. When we talk about the section capacity, don't forget that you have to check whether the member is prone to the local buckling or not. Is it prone to the local buckling? You have to adjust them by using the concept of the effective areas to what we discussed to adjust the portion of the steel member, especially for the infill. But for the encasted, you don't need so because it has been prevented from the local buckling, right? But on the other hand, if we come back to this diagram again, if the standard rate ratios become more than the limit, they're saying that you have to adjust the capacity, and you are not allowed to use the full squash load capacity. The reason for this because it's not safe, so you have to time with some type of the reduction capacity. The reduction capacity has been calculated based on these formulations, right? And you can see that, okay, it's just come and calculate according to this, the size factors and the eta factors here, and the R is the radius of gyration. So you just use this 3 formulation to use and approximate the reduction capacity according to the global buckling, right? And in this theoretical concept, we use it for the elastic analysis. So basically, the line that you have, which is the line here, when you adjust them, is quite conservative because we don't allow them to develop the stress up to the full ultimate strength. So the stress diagrams that distribute to the cross section still be the triangle stress diagram. So it doesn't form the full rigid classic diagram. So if you use this formulation, it's too conservative, right? So that's why in this area for the slender columns, it's still very active areas. There are so many publications in the last 20 years. They come and try to predict the capacity of the column, especially for the slender column, to be close to the real, right? But to what has been suggested in the code, the way how we take into account of the slenderness of the member is similar to the concrete. It's similar to the concrete. So what it means, before we move to that point, the example number 1 and the example number 2, they describe how you adjust the axial force capacity based on the elastic analysis, right? And we have some adjustment according to some of the reduction capacity factors. And I talk about this. So the factor that we talk is this factor here, they call as a slenderness parameter. So the slenderness parameter is sit between 0 and 1, and the maximum is you go up to 1, right? And the more that you have the member slenderness, the less of the factor here becomes, because you are allowed to use less capacity. So you have to reduce the capacity of the squash more. But in the design, so it's tend that, of course, this is the concept of the effective length. Everyone have been aware of this. But what we use in the design procedure, we tend to use in the similar way as what you did in the concrete designs, right? Because this is quite being appropriate for now. In the concrete design, they're saying that you have 2 types of the survey, of course, in the steel design as well. One they call as the braced column, the other one they call as unbraced column. Unbraced is mean it has been allowed to survey. So more likely this one will be more critical, because if you think about in terms of the effective length, the value of the effective length will be more when we have the same physical length with the braced column, right? And in our exercise, right, we could not cover for the whole, we can cover for some, but to use the same concept of this, we will discuss about the case for the unserrated. So we only discuss about the term for the braced column, which is quite makes sense as well. In most of the building, if you have so many bays, or the building is not too slender, basically the column that you look at, we can consider them as a breasted column because the behavior of them is tend to become non-survey, right? And this one is a non-survey case that we're looking at in this course. And they're saying that the limit to consider whether the structure that you're looking at in terms of the member buckling, whether it's become as prone to the, or it's called as a slender column, or it doesn't, or it's called as a stocky column, you use this criteria here. So they say that it is the ratio of LE over R had to be sit less than either the value of 25 or the formulations here, which one give you more, you take that one. And you may have the question of M1 star, M2 star, similar to what you did for the concrete. Remember, when we look at each of the column, we're looking at that in this column, how much of the bending at the top column and how much of the bending at the bottom column. We use this as a bending capacity. And we treat between which one is give you more value. We give them the name as a M2 star, which is this one here. And between this top and bottom moment, which one give you the less value, we give them as a M1 star, right? And that's why the ratio on in terms of the absolute value, the ratio between M1 and M2 has to be always less than 1 and sit between the value of 0 and 1. Then there is the sign come with them as well, which they're saying that it is formed as a single curvatures. You're saying that this is a negative sign. If it's come as a reverse curvature or the double curvature, as I draw quickly here, you call them as a positive signs. And you have a look. If we having a single curvatures, the parameter here we have the value of the negative signs, right? So it's subtract with 1. So basically, this will reduce the limit to check for the slenderness of the member. But if we have the double curvature, which is stronger, you have the positive sign, so it's increase the value of the limit, which is makes sense. The last term is the ratio between the F' and you have the star as well. Don't forget you need to come with them, which is the load factor as well, right? And we use in all the designs. So you have to looking at the load code in each of the country that you're looking at, the load specification they tell in the table that if you want to design for the axials or in this type of scenarios, not the axial, in this type of the scenario, what is the combination that you have to look in terms of the load capacity factors, and you find the worst case scenario. And then you extract the N star, which is the axial force. So they want to look the ratio of the applied axial force to the capacity at the squash load. This is the squash load, right? So it's a pure axial force, and you reduce them by 60%. And what they do, they look at the ratio of this is you apply the column with quite a lot of the axial force until it's almost reached the limit of the squash load. So basically, you will have this capacity more, and then this term will become less. So it will reduce the factors here, right? So it's easily prone. The more that you have the compression force, so the easier that you will have the column to be prone to the slender column, right? So you have to check this first. If the ratio of LE over R is sit less than these two values, so basically the column that you're looking at, it doesn't be sensitive to the slenderness. So the length of the column is not considered to be high compared with the size of the section. So you can design them as a short column or the stocky column. But if the ratio of this more than these two limit here, of course, you have to adjust further because the column that you are considering is called as a slender column. Okay, so this is the concept that we use in the design. And to come and we start to look into the formulation. So what I have to say, apologize, is this is wrong. So basically the value in the single curvatures here, this is the negative value. And when we have the reverse or the double curvature, you have the positive values, right? And they just, excuse me, they're describing that this is they call as a secondary bending moment, as I mentioned before. So if you talk about what is called as an applied force, you have already this this diagrams, but because of the slenderness of the member, you have the value of the bending to become more, and the range of how much is more is called as a secondary moment. So to take into account of this, right, and in this effect, we want, I say again, this is for the braced column. So when we talk about the braced columns, once again, we talk about the column that has been restrained in top and bottom, and you having an applied force, and you got the bending moment as well. You can have them as a M1 star or M2 star, is okay. If I want to make it match to the figure to what you have below. And when we have in this case, the consideration that we have in this code is only for the P data effect, and we call them as a small data. It's not the big data, because this small data, we make the bending moment that you have, which is the maximum of them, to become I don't draw it. I just say that we use this equation. So you magnify them, the value of the maximum bending moment, and this factor is taken into account of the secondary moment or the P data. Remember, when you learn about the secondary effect, you have the term of P data and the small data, and you have the P and with the big data, right? Big data. And this one is for the unsurveyed. We call them as a non-survey. And this one is coming from as a survey, right? When you talk about the survey columns, you have to take into account of both. But when you talk about the non-survey, we only take into account of the top one, right? But when you talk about the survey column, you have to take into account of both P data and the P big data and P small data. Okay. So I should talk in these terms, maybe better. He's saying that we have a non-survey so you discuss about the concept of the P with the small data, but when you're considering for the survey columns, you talk about in terms of the P small data, and also you have to consider the P big data. So that's why if you look into the concrete code, they have another factors times to the axial force as well, but we don't consider this because in our discussions here, we discussing about the non-survey columns, right? So that's why we only consider the parameter, which is the data B. Then the calculation of this is similar to what you did in the concrete design. So you have the Km. The Km is the formula has been told. The beta is the ratio of M1 over M2. And don't forget the size of the beta become negative when you have the single curve measures. And the sign of them, we have the positive signs when you have the double curve measure. Having the sign of negative. If you have a single curve measure columns, the sign of the betas become positive if we have the shape of the column to become double curved wedges, right? Always. And the less of them, so you got the term Km, right? You have N is the axial force that is applied, and you don't take the factor as all. So this is the nominal factors. But if you want to take the N stars here, so what I suggest is this. If you want to take this to be the N star, you can use this factor as well, but you have to use the N star if you want to use them. Divide by the reduction capacity factors divided by the capacity of the column under the buckling. When it's under the buckling, right? So we use the formulation that has been told according to the Euler buckling formulation. But the way how we determine the parameter EI, right, is depend. In this case, we use the EI is a combination of the EI from the steel plus 80% of the concrete. The reason why they reduce the EI, which is the stiffness of the concrete, by 20%, so they use up to 80% because they take into account of the crack in the concrete. So I just give you considers the crack in concrete. Right, just keep in mind. So the value of how much you should adjust the cracks is depend. Normally, let me excuse me. Let me talk about when I believe most of you may haven't designed the building as yet, right? But in the realities, let me discuss about this. Is just come from if you start to do the work, this will be the question that you will be asked. If you had to design, analyze a building, basically, assuming that this is the reinforced concrete building, right? We're saying that this is the reinforced concrete, which is the RC building. Some of you may know, right? Some of you may not know. So if you use the question is that how much of the stiffness you should put into the member. You use the any of the package, and you use the excuse me, you use the what's it called, the line element, and you just give the stiffness, which is EI, according to the material you use. If it is a reinforced concrete and you use a full capacity of the EI, which is stiffness, so you just predicting the structure having the stiffness of the perfect. So it means you assume it's no crack. Normally in the EI of the concrete, right, they're saying that, especially when you input in the material property for the Young modulus, they suggest that you should use the ratio around sit between the ratio that you should have. It should sit between 0.4 up to 0.6 of the actual EI to take into account of the concrete buckling. Sorry, the crack in the concrete, not the buckling. And normally what we do is that the ratio of 0.4 to 0.6 we use in the column, right? And in the beam we use around 0.8 most of the time, or you can reduce it to 0.6 to be the same as well. And if you reduce the stiffness, of course, when you analyze the structures, you will see that the deflection will be more, right? So this is real because when you apply the force to the structures, you want to consider in terms of the worst case scenario. So that's why you should reduce the stiffness of the section. So I'm saying that this is we call as a stiffness reduction. But when you talk about the analysis of the concrete, sorry, of the steel structures, you don't need to, because the steel, it doesn't form the crack at all. So you can use the full stiffness in the steel, right? This is the benefit of the steel. So that's why when we come to our case, when we want to consider the buckling, the elastic buckling load of the columns, there are a couple of the concepts that you can take. One of these is that you can take the combine between the stiffness coming from the steel and the stiffness coming from the concrete, and you might just reduce the stiffness of the concrete by some certain percentage. If you take 0.6, of course, it will become quite conservative, but we do not recommend so. So you should use, because the composite, because of the composite part, it's either provide a partial confinement or the full confinement to the concrete. When it's provide the confinement to the concrete, either partial or the full, is try to reduce the crack happen in the concrete. So that's why the code just suggests you to use the reductions 80%. So you just drop them by 20%. Normally we use 60% in the pure concrete, right? And so in this case, so that's why we use this, and we just substitute the stiffness, right? That's come from the combination of them, and we calculate them by using the Euler buckling formulations, and then you got the column critical, or the N, which is we define for the critical. It means this is considering the buckling, the member bucklings of the columns. And what is happening in this case is this: when you consider this is the loading line you have, right, which is not the loading line, the interaction diagrams, you're having the loading lines to what I told you, which is come from the perfect case, is for the stocky column, right, which is it doesn't affect that. This is my handwriting, right, so unaffected by the slenderness. But when we have to adjust, for example, if we talk in terms of the line before you considering right, because this is in the same lines as after you adjust it. So at this point, the coordinate that you have under the unadjusted, so we haven't adjusted for the what's it called, the moment magnifiers. So you would have this one as the M and N, right? And we define M equal to the N times E. So that's why you can draw the linear line, and we say that this is the loading lines here. But when we have the column that becomes slender, the loading line that you have will change and will form as a nonlinear curve here. Why? Because the formulation of this line here, if I take into this point, the formulation of them is delta B times with M and N. And of course, you can describe these terms as a delta B times E, right? And times N. So you would have these terms that been affected, right? And especially the one here. So in order to check in the real design, so it's quite straightforward. You just get the failure line first, and this one we obtain from what we assuming that this is the section capacity. And if you have the stocky columns, you can just simply check them, right? Having the point of M and N, of course, you know if it sits inside the section capacity, so it's safe. If it sits above, so it's non-safe. But if you have what is called as a slender column, the course suggests you to use the factors. This is not clear. I take this off. The course suggests you to use the factors, and the factor is called as a delta B, which is the moment magnifiers. So you have to time them here. And the calculation for the moment magnifiers has been described by this series of calculations. So you will see very clear that the term of the delta B has been written in terms of what is called as a axial force. So when you're looking at the formulation of this, which is this is the formulation of this curve here, is for the nonlinear equation, because in the formulation for the delta B we have another n term inside the formulations. This one is fixed, the n critical is fixed, the term that is valid is n, right? So you need to write the function. For example, if I want to see the function of these equations, I'm saying that the functions of the m will be written in terms of n, right? But n here, this is will become the nonlinear equations, which is the km divided by, we have n over n critical time with E, which is the eccentricity, is the fixed value, and time with n. You see that in the curve here, you got two value of the n. So that's why it's formed the curve here to become nonlinear, right? And when we do the design, we just check whether this, when you magnify the bending moment with the delta B, it still satisfy the section capacity or it doesn't. If it's already satisfied the section capacity, so it's good. So you okay, they said okay, the design of it is good. But if it sits above, what you do, you have two choice. Either you increase the size of the column, you increase the strength, right? And this is the concept of the design. So it's quite simplified, very, very well simplified method. Before we look a bit further, do you have any question first? So let me move this to the side here. Any question first, and then this is the example. Any question, please? Feel free to ask me the question if you have. Okay. So if you don't, okay, we have two examples, which is behind here. I will not go through all of this because what is happened, let me tell you. The example number 3, they're saying that you have the, what is called the concrete infills. And the size of the column is 1 meter. The thickness is 25 millimeter. The first thing of all, you have to check whether the column that you look at is a slender or it doesn't. So in this case, they're saying that this is slender, right? So in this case, it doesn't tell you how much of the axial force has been given, right? But to be more conservative, so basically you can use a primary, and normally we use 25. So you know, I will tell you the limit, and the limit that we keep using, we're using from the code, which is 25, or these equations here. And if in the exam, I will tell it's clear, okay? So this is the limit we're talking about. So let me come and say that, okay, this is the limit we use. All right, let's just keep this in mind. And rather than you use 22, you use 25 to be more consistent for this case. But okay, assuming that this is the standard column. So what you do, they give the geometry of the column, and they're saying that, okay, for this type of columns, you have the height of the column is 8 meters, and this is the continuous column, and you have the pin, right? So normally in this case, because it's a pin, so it's zero moment here, it's zero moment here. So basically, the model of this column is like you have the pin restrained. You have the pin restrained. So the physical length we give you, normally we give you the effective length, right? Which is, you can take LE equal to 8, unless it has been told the value of the LE to be some values, right? So that's why I have a look here. They're saying that they use the LE in this scenario equal to 8 meters, right? So we consider the worst, which is the highest column that we're looking at. And the length of them, you just calculate the stiffness of the concrete, right? Okay, we have the envelope, which is this cross-section diagram. So you just calculate them based on the section capacity. Right, you start to calculate what is called the I, which is the second moment of areas. You calculate the steel second moment of areas. You calculate the effective stiffness equations, right? So you don't forget to reduce 80%. You calculate the Euler buckling at this critical member, and you calculate the moment magnifiers. And what you know is that the M, right? This is from the loading lines, right? They're saying that they calculate how many story, right? The force we taken in this case, and what is the minimum. They use the minimum eccentricity in this case. So that's why you got this calculation for the bending moment and also for the axial force. And what you do, right, based on this column, you can calculate the interaction diagram of this easily. So that's why you have the envelope lines here, and you have the line which is the thick one. The thick one, this is coming from what is called the loading line, which is from the stocky column, and you have the thin one. This is when you multiply them with the moment magnifiers, right? And you just check in this case if when the line here is going to hit the boundary, so you can tell that what is the maximum capacity that the column can be taken, right? So you have to basically use the Excels, or use, if it is a linear equation, you use two linear equations and you find the intersection point between them, right? And then you can, not the linear equation, you have the non-linear equations here, you have the linear equations here, and you substitute the equation so you can get the intersection point between them. And you can tell that, okay, which one it will give you the failure. If the question doesn't tell you the fault and they ask for what is the maximum fault they can apply to, you have to do this way. The best that it describes, another equation, another example is this. You have the same section for the columns, but we change the thickness to be 40, right? And we do the calculation once again, and we say that we assume that the effective length is 12 meters for now, not 8 meters, so we increase the height. And we're giving you the E value, we're giving you the ES. And the first thing you have to obtain the column curve approach, and you have the interaction approach. The column curve approach will give you the nonlinear lines and so okay. And the interaction curve approach will give you the 4 point, right? 4 points is here. 1, 2, 3, 4, the column approach. So you have to obtain the nonlinear curve by varying what is called as a drastic neutral axis depth. They're saying that they assume the beta is quite conservative. This is the single curve wedges, right? And they assume that M and N they are the same. And this is the equation for the Km. And so on the purpose of this, they want to calculate the delta B, right? This is very straightforward. And this is the N critical. Then they can write the equation as what I showed you before, the applied moment in terms of the axial force. And you're seeing that in the formulation, they got two of the N values. This is, of course, a nonlinear equation. So when you plot these nonlinear equations, you can plot them in the Excel. So what is happened is that you will have the nonlinear curve, right? Sorry, it should be nonlinear. Okay. And they just find the intersection point to determine where is the failures, right? So the failure is the point is cut between, this is the piecewise linear. They come from the intersection diagram, so they come from the piecewise linear. In the diagrams. And if you want to make it more precise, you can draw the nonlinear as well, but you have to use a column approach. So basically sorry, I cannot get the lines to be correct, but I can simply draw with my hand. If you vary the neutral axis depth, you will have the nonlinear. So you might see that the capacity you can have at the most, if you compare between the interaction diagrams and also the column curve approach. So basically you compare with the nonlinear diagrams here, the failure that you can have, which is the maximum location, the maximum applied force in this point will be more, right? But we don't know how much it is. So you have to find the intersection, the intersection between these two lines. But of course, this will be more than what you have here. This will be more, right? From the piecewise linear interaction diagrams. The reason why I did in the last of all, I like to thanks for your patience for the last 7 weeks that you come along with the whole journey with me. It's quite very time consuming for me as well for this semester, because I prepare everything's new. And this is the first time that we deliver the composite course, and I hope you satisfy them well. And if you want to suggest a comment, please let me know. So I am very happy to take them all, and so that we can improve the course for next year. And the last of all is that I wish you the best, right? So this should